So now, within dispersion forces, there are different levels or varying strengths. So, two things determine strength of dispersion forces. Okay, and those two things are shape and size. Okay, so let's talk about shape first. Okay, and I'd like you to imagine, if you will, you've got a pair of tennis balls covered in Velcro. Okay, so those things are covered in Velcro of opposite types of Velcro, of course. And you stick them together. And if you do that, all you get is about that much stick. Okay, so these are going to be easy to pull apart. Right? A couple of tennis balls stuck together, that's going to be a no-brainer. Easy to pull apart. Now imagine, if you will, instead, you have a couple of 2x4s. Again, covered in Velcro. You stick those together, and you've got all this interaction. Okay? Which is going to be more difficult to pull apart, the tennis balls or the 2x4s? The 2x4s will be harder to pull apart. Okay? So how does this relate to chemistry, Dr. Lyon? You may ask, and are probably throwing things at your screen. So let's describe. So imagine I have a molecule that looks like this. Okay, and all those carbons are surrounded by hydrogens. But the important thing is that we have 5 carbons here. Right? Or one that looks like this. Also 5 carbons. Right? Which will have the stronger forces? The long, flat one. Much like the 2x4s in the example. The one on the left is much like the tennis balls, covered in Velcro. The one on the right is much like a 2x4, covered in Velcro. So you can imagine another molecule sitting right above it, and you've got all this interaction. Okay? So dispersion forces it's a bit like Velcro. You've got a little bit of a stick, and then they can come apart. Okay? So the other thing that affects dispersion forces is size. So the idea with that is that bigger molecules have more electrons. They have bigger clouds. Okay? So size is important, and you can think about it in terms of molar mass, right? But let's imagine that I've got one scenario here, and I've got this interaction, positive, negative, negative, positive, okay? Or I've got a bigger molecule, right? Over here I've got 3 negatives. Over here I've got 7 negatives. We have a much stronger interaction with the larger molecule. Okay, so just based on where things are on the periodic table and how much they weigh, we can determine what relative strength of dispersion forces. Okay, so now here's the important thing, is that stronger forces, up here on the upper left, Stronger forces mean higher melting points and higher boiling points. So greater temperatures to melt things, greater temperatures to boil things. And you can think about it in terms of what happens to the molecules when you boil something. It's an easy one to imagine. Imagine your liquid state, all your molecules are stuck together by certain levels of intermolecular forces. And in order to make that liquid become a gas, in order to break those intermolecular forces and let that individual molecule go flying off on its lonesome, or on its freedom quest, or whatever you want to say, you have to provide enough energy to break its intermolecular forces. Okay? So if the forces are strong, that means that you have to put a lot of energy in order to break those forces, right? A lot of energy means that you have to raise that temperature up higher, right? Cook things on the stove longer, so to speak, okay? So on that subject, let's look at what we have here. A has 1 carbon, B has 2, C has 3, D has 4, and E has 5. 1 carbon versus 5 carbons. Right? So just based on size, right? Because these are all relatively the same shape. They're all just making in chains. 5 carbons wins. Oh, wait, sorry. I should probably edit this, but I probably won't. Sorry, this says lowest melting point. This is just like being in class, isn't it? Right? So lowest melting point means weakest forces. Right? Sorry about that. I got a little backwards there. So the weakest forces is the 1 carbon, the methane. Which of the following is a liquid at room temperature? And that's going to be the one with the strongest forces. Okay, it actually takes pretty strong intermolecular forces to keep a liquid state at room temperature. So looking at these 4 choices, A has 1, B has 2, C has 3, D has 4. I almost did it again. Sorry. Strongest forces are going to be with the 4 carbons. Right. Looking at the structure of ammonia, what is the strongest intermolecular force for liquid ammonia? So we know that dispersion forces are 1. Do we have any ions for B? Do we have any ions available? And the answer is no. Right? And if I'm talking about ions, I'm talking about something like a sodium hanging around, or a chlorine hanging around, or a potassium hanging around. That's what I'm talking about when I ask if there's ions present. Okay. So dipole-dipole forces, right? So if I look at ammonia, I've got the nitrogen is more electronegative, so a general pull in this direction because there's nothing pulling back down, which means that it's polar. So if it's polar, dipole-dipole forces are an option. Do I have hydrogen bonded to oxygen, nitrogen, or fluorine? The answer is yes. So hydrogen bonding, and we're not even going to discuss anhydrous dispersions. There's no reason. Okay, so of these 3, the hydrogen bonding wins. All right, so let's take a look at the structure of formaldehyde, as shown below. What is the strongest intermolecular force for formaldehyde? So always an answer, I should say. We don't have any ions present. Do we have dipole-dipole forces? That is basically a nonpolar bond. Those carbon-hydrogen bonds are doing nothing. But I do have a strong pull to the oxygen. So this is polar. Now, do I have a hydrogen bonded directly, and that's the important part, do I have a hydrogen bonded directly to the oxygen? And the answer is no. Just because I have oxygens and hydrogens in the same compound does not mean that I have hydrogen bonding. So between these two forces, dispersion or dipole-dipole, dipole-dipole wins. Which has the highest boiling point, and by this we want strongest forces. Okay, and these are all pretty much the same. They're all something bonded to a chlorine. Okay, so in this case, I want to look for the heaviest. Okay, and in which case, if I go through and I look, I'm going to find that boron chloride, or barium chloride, is the heaviest of this group. Okay, so here's the point where we're going to start talking about gases.